lost. Okay, let's get started. So today's lecture, I'm going to spend pretty much entirely on homework 4. So that'll be pushed out sometime tonight or tomorrow morning. I'll post on Piazza when it's out. And then it will be due a week from next Wednesday. I'm going to compress the schedule for the last 2 homeworks a little bit because I'd like to get them off your table so that you can focus on the projects by, I'd like to get them all in, which is 4 and 5, done by early November. So we're going to talk both about the algorithm, about kind of how the software is set up, and then I'm going to spend a fair amount of time actually walking you through how the makefile is set up, because this is the kind of next version of how we do build that actually completely implements what I would like you to do for your projects as well. So you'll see what goes on there. Anyway, but before we go into that, I'd like to clear up something from the last time I lectured a week ago, which I realized was just gibberish, which is kind of how matrix multiplication, the DGEM benchmark, interacts with cache. And it's really interacting with L3 cache. So from last week, we were talking about matrix multiply. And you have written or are writing for this week's homework something that does that implemented as a triply nested loop. So here's the way to understand what it is doing algorithmically, is that if you're multiplying the matrix A times matrix B, what you're doing is for each column of A, you take dot products of that column with successive rows of B, and then you stuff them into the appropriate column of C. So that's what matrix multiply does when you do it as a triply nested loop. So how does that look algorithmically, depending on how you order the loops? Well, with one ordering the loops, what you're doing is you have a column of A that you read in, and then you're reading in the rows of B, one after another, taking that dot product and storing it. So you go all the way down here to the end, from row 1 down to row n. How does that interact with cache? Well, let's say we have a very simple cache eviction policy, that the oldest, i.e. the least recently used read data, gets overwritten when you run out of space. In that case, then there are really only 2 possibilities, and they change rather discontinuously. If your entire matrix B fits in cache, what happens? Well, you take you bring in this column, dot product, dot product, dot product, get to the end. Now you bring in the next column. Well, B fit inside of L3 cache, so it's still there. So now you're just reading it from L3 cache again, and you do this over and over again until you've completed until you finish the complete matrix multiply. So if B fits inside of L3, then you're fine. You only read it from main memory once. If not, then it's kind of a discontinuous and catastrophic failure. That is, let's say you do this row times this, or this column times this set of rows, and now you come in and read the next column of A. So what would you have done? You go back up to the top and read this row. Where is it? Well, it's gone. The reason it's gone is because this was the row that you had read the longest time ago. So all of these rows here were read after this row. So this row, and B doesn't fit in cache anymore, so something from B had to be evicted, and it would have been this one. So it gets evicted, and you end up having to read it in again. And this just happens over and over again. For every row, you're reading it in over and over again. So if it fits in cache, everything is great. You are constantly, you read it from cache all the time. If it doesn't fit in cache, it's, you're reading now from memory over and over again all the time. There's really not much of an in-between. So let's see how well this actually works. So what I did is I took my version of the example on my laptop, and what I'm doing is I'm plotting. This axis here is the performance measured in megaflops per second. And this axis down here, okay, that is readable, is the size of the matrix, but the way I've labeled size of the matrix is instead of having it as a number n for the size, the axis is actually labeling the size of one matrix of size, whatever n is, divided by the size of my L3 cache. And in this case, my L3 cache is 3 megabytes. So what we see here is that we're up around 1800 megaflops up here for small sizes. Down here it's going from 0 to 0.2 to 0.4. We see a little bit of decline, a little bit more noise, and then all of a sudden here, at around the matrix size, which corresponds to one of the matrices fitting it takes up about 70% of cache. All of a sudden we fall off the table, and what's the good news? What's the bad news? Well, the bad news is that why isn't that 1 or something very close to 1? Well, as I said, my cartoon for the cache eviction policy was a cartoon. There are other things going on about what other things are being left in cache, how much of A is being left in cache, what's happening to C on going out. And there are other things that may keep us from using all of cache. I don't know how cache behaves in detail. I have a cartoon. However, that said, with this as my cartoon, it's pretty good. I'm saying, well, if my matrix stays below 2 megabytes, which is 70% of cache, I can fit inside of cache and I get very good performance. As soon as I go outside of something that is, somewhere between a half and all of cache, the matrix being between a half and all of cache, then I fall on the floor. That's actually, as performance models go, of performance cartoons go, this is actually a pretty good result. If I would encourage you, if you're interested, to run the same experiment on whatever machine you're running on and see how good a result you get. How good a correlation you get between when you fall off the floor, fall off the table, and when you get and the size of the matrix relative to the size of your L3 cache. Okay, so now on to homework 4. Homework 4 is going to be particle and cell methods for vorticity. I'll first go through the algorithm, and then we'll spend a fair amount of time on the implementation issues. So these are regularized particle methods. We have a particle method for vorticity transport in 2 dimensions. dx dt is equal to u of x of t. U of x is equal to one way of stating this kind of integral equation form. The velocity is given as the vorticity, as the sum over particles of vorticity times the gradient perp of the Green's function convolved with a smoothing kernel, and that's equal to the sum over k of omega k u epsilon of x minus xk, where u epsilon is just given by the gradient of that smoothed out kernel. So for epsilon equals 0, what is our smoothing function? Well, it's 1 over epsilon to the d psi of z over epsilon. As epsilon goes to 0, this becomes a delta function, and this becomes somewhat singular. So what we have to do is to do some sort of regularization to keep the singularity from causing stability problems. So what do we use as a regularized potential? Instead of having a delta, we have some sort of smooth function that has integral 1 and some nice smooth properties going out from 0 to 1, and then it's 0 outside. So if we smooth the Green's function that way, here's what our method looks like. So we can think of it as regularizing actually the potential induced by a collection of delta functions. So you have omega, which is omega k times delta of x minus xk. Here's your stream function, g convolved with omega, that's omega k g of x minus xk, where that's the ordinary Green's function. And then you regularize that to say it's g epsilon convolved with omega, where g epsilon is, as I said, it's the convolution of g with this nice regularizing thing. Now, notice that this is zeta of z is a function of absolute z of the radius from the distance from the origin, which means that these regularized things can be computed analytically. They're, it's separation of variables for solving Poisson's equation, and it's pretty easy. And then finally, your velocity field is the gradient perp of the stream function. So that's what we are trying. So that's our. So you can think of this as here's one level of regularization that we introduced to the problem that allows our particle methods to be well behaved. Now we're going to take a particle method that discretizes the regularized form of the equations and use particle and cell on that. So what's particle and cell? Reminding you, you start with a collection of particles, each of which induces a contribution to the stream function at any point in space by convolution. We introduce a grid, and in particle and cell, we replace the continuous convolution with discrete convolution on a rectangular grid. We replace omega k delta of x minus xk, which is with omega sub I of, which is on each grid point is the sum, is the contributions from each particle of a regularized by h delta function evaluated at grid points. Then we compute the stream function on the grid as a discrete convolution with our original Green's function. And then we interpolate the finite difference approximation to the velocity from the grid to the particles. That's pretty much what we described before. Now I'm writing it down in complete detail so you can, this is what you'll be using as a reference to implement this. Given particle locations, we compute a velocity field at these locations by the following process. First is deposition of vorticity onto the grid. We have some regularized delta that is defined as a function of its argument of x, and then we say omega k delta h of ih minus xk. Sum over k is the function, is the vorticity at grid points I. And then we have psi I, which is the grid-based stream function, and that's just obtained by taking a convolution of g with omega j, and that's going to be the regularized g. So we have two regularizations here. One is the thing that's regularizing g, the Green's function, and the other is this deposition function of taking vorticity and putting it onto the grid. They're both there, they're both active. And you need them both, because if you don't have regularization present in g, what happens if your particle actually happens to land on a grid point? Well, you have a singular solution there. So you have to introduce some sort of regularization. And then you, so you do this convolution. We know how to do that fast using Hockney's method. Then we compute the velocity field by taking the gradient, the finite difference approximation to the gradient perp applied to the stream function. I've written that out here. The derivative in the x direction is just center differences divided by 2h. Derivative in the y direction, center differences divided by 2h. Then finally, to get these velocities on the grid interpolated back to the particles, we again use this deposition function, this delta h deposition function, to get ui onto u of xk. And in all of these things, delta h of z rather than being a radial thing, is going to be something that's well suited to particles. It's a tensor product of two one-dimensional things. So let's look at what the one we're going to use. The one we're going to use is a function that is piecewise linear. It goes from 0 at -1 to 1 at 0, and then back down to 0 at 1. So this is there are other things you can do that are less accurate. There are other things you can do that are more accurate, but it's the blue one that we're going to be using. And that's in one dimension. To get it in more than one, to get it first of all on a grid of spacing h, we scale by h, and then secondly, to get it in 2 dimensions, we do a tensor product. In fact, when you look at it, how you end up depositing things, it's going to look like bilinear interpolation from a point or to a point. So that's the algorithm, and in the homework description, I'll even put in more detail of exactly what you do. So, what goes into this algorithm? First of all, how do we initialize our particles? What we do is we put them on a grid with mesh spacing HP, which is the mesh spacing for the particles. Again, you think of particle methods for vorticity or for in phase space for anything where you're solving an advection-dominated PDE as being Lagrangian methods on the Lagrangian grid. Well, this is the discretization for our initial Lagrangian grid. So what is the relationship between epsilon, h, and HP? Epsilon is the smoothing distance for our Green's function, h is the mesh spacing, and HP is our particles. Here are the choices we'll be using here. HP is going to be h divided by some positive integer. 2 or 4 typically is what we use. So we have 2 or 4, but order 1 particles per mesh point per direction. And then epsilon is going to be equal to h. So we'll use the same regularization that we use that's implied by the grid to smooth out our Green's function as well. There's certainly historically the really good convergence theory, the earliest convergence theory for vortex methods, has no regularization, no grid. So the grid introduces its own short-range regularization in addition to that regularization. However, the good theory also used the epsilon, this regularization distance, as being order of a fractional power of HP, which means order of a fractional power of h. So can we, and that seemed at the time to be required. Well, you can recover those kinds of methods effectively by using something that looks like a p cubed m method. So you can have somewhat longer range smoothing distances. And that's actually, again, I talked about that in an earlier lecture. That was the method of local corrections. But it appears that we don't need to do that anymore. And in fact, the theory has undergone a lot of work in the last 15 years because of the interest in doing things that are more like PIC methods for vorticity. And I think that these issues have been largely resolved, that you can, this choice of parameters all hangs together from a theory standpoint. So, how are we going to break up the work here? We'll provide an implementation of Hockney's algorithm for computing the discrete convolution by the regularized Green's function. And we will also provide the templated fourth order Runge-Kutta class that I've already discussed with you. You will implement the rest of the particle methods. Deposition of charge and calculation of velocity field. That corresponds to one of the classes you need for Runge-Kutta, and the template classes for the particle state and particle increments that are appropriate to pick. So let's go through what you're going to get and then what you're going to have to provide. So recall, this is what you're going to get, which is an implementation of fourth order Runge-Kutta that is parameterized as template, that is a templated class. It has three template parameters. One is x, which is the state of so that's where all the particles are and whatever other information you need. One is a class F that just computes the right-hand side, that just computes when you express things as ODEs, it's the right-hand side of the ODE. And then one is a kind of helper class. It's something that you can store increments of state in. Now, the important thing here is that of these three things, only one of them has a kind of persistent existence. So when you advance by one time step, so the main program will be calling advance, for example. To advance by one time step of fourth order Runge-Kutta, you pass in time, you pass in your time step, and then here you're passing in state. So you actually know, or the calling program, the driver actually knows what state is and can actually manipulate state outside. So it can do the, set up initial data, it can set up other information. All of the things like dx and the things that are of class increments of the solution, and the thing that is of the class how to compute the right-hand side, those are all internal to RK4. So if there's any context that you need, for example, how do I get in what my smooth kernel looks like, what G epsilon looks like? That has to come in through state. There is no other mechanism to bring it in other than through state, because these other things don't have, these are generic. They do not have enough information by themselves, as you'll see shortly, to find out what it is, except by the definition of, say, F, knowing that it's going to have access to X and be able to get any persistent state information from X. So here's some particle classes. We start out with classes for a single particle. So you have a single particle, and I still haven't gotten rid of all the reals. It should be array of double dim, not real. You have, so this is, how do you define the increment of the location of a single particle? Well, that's dx. And you have an array of tuples of size dim. In this case, dim's all going to be 2. So of 2 tuples of doubles. And then we have a couple of functions which tells you how to increment a dx and how to scale a dx. That class is going to be provided to you. And now you have a class particle, which has it also has an array of tuples of doubles. And then you have a way of incrementing that by a dx. So you can increment displacements of particles by itself, so you can add 2 displacements together, but you can also add a displacement to a particle, to a state of a single particle. Now, the next piece of technology we have here, next class that you will be provided, no, you will write these, but you will be provided the header files. So particle set and particle shift are the collections of, are either the increments in a collection of particles is what particle shift is, and particle set is the thing that describes the state of all the particles. So here in particle shift, this is the thing corresponding to, in our RK4, dx. You have a vector of increments of particles. So these are increments of particles. You know how to initialize, you know how to increment, you know how to scale, and you know how to set to 0. So these are the functions that are part of the contract that RK4 knows about. RK4, whatever you're defining as your dx in RK4, has to know how to call these functions and what they mean relative to particle set and the various scalars. Now we run into a little bit of a technical problem, and it's a common one in C++. That Particle shift needs to know, takes as one of its, for one of its member functions, takes as an argument a particle set. Now you will see shortly that particle set takes as a member functions, one of its arguments, a particle shift. That's what's called as a circular dependence, and compilers get very confused by such things. They really don't, C++ compiler doesn't know what to do with it, and it'll return an error. And the way that that gets solved in C++ is by something called a forward declaration. That, so you have your definition, your declaration of particle shift, and we have all these functions here. We're allowed a restricted amount of access to what a particle set is. We can tell it that a particle set is a class. We can't tell it anything about that class, but we can tell it it's a class. And that's enough to do most of what we need to do. Why? Because if all you know that particle set is a class, the thing that you know how to set up is pointers to particle sets and references to particle sets. As long as you know that those things exist and have a name, you can use them in header files. So all that the particle shift declaration is allowed to know about is the fact that particle set is a class. So you can hand pointers to particle sets, you can hand references to it. You can't add values of a particle set to it. So why is that? Well, think about what call by value does. It makes a copy of the object. Well, the copy of the object and puts it on the stack. Copy of the object means you have to know the size of the object. And that's something you don't know at this point. All you know is that it's a class. By contrast, sending a pointer to such a thing, that has fixed size. Pointers all have the same size. So you can set the memory up for that on the stack and you have no problem. So let's now look at particle set. That corresponds to the template class X in RK4. That's your state. It has, these are the things you're going to want to define for it. There's a constructor. The constructor is not used inside of RK4. It's the thing that that defines what particle set is, and it's defined outside of RK4. However, you're going to pass in some things, or the driver program is going to pass in some things that have to do with the Hockney algorithm, the convolution kernel, the thing that allows you to that defines the smoothed out Green's function. The box that over which your particle and cell method is defined, mesh spacing. You need a real value for what the low corner is, so you can compute absolute locations relative to your box, and you need to know what a sub m is, and m is the log of the number of mesh points, log base 2 of the number of mesh points. So we're always going to be working with power of 2 number of mesh points. So what else are you going to have to provide? You provide a constructor, you provide, you have a default constructor. The state that you're going to store is a collection of particles, is a vector of particles, a vector of things of type particle, single particle. Mesh spacing, a box defining the array, again, the array of reals defining the low corner, and then this Hockney. There's a Hockney class here that implements Hockney's method for discrete convolutions. And then finally, you have to define increments. So given a particle shift, how do you increment your particle set? How do you add the total effect of the time step? So this part here is the contract. This is the part that RK4 knows about and will call. And then finally, implements the template class F in RK4, the thing that computes the right-hand side. You have a constructor, a default constructor, and you have an operator, so that if you have something of type F, you have, or of type particle velocities, you'll see that you just take that and apply it to particle shift, the time in dt, and particle set. Now, particle velocities has no state, only a default constructor. So that means any of the persistent state that you need to have to evaluate the right-hand side has to come in via particle set, via a state. This is one of the reasons that there was really no point that we just went ahead and made all the member data of particle set public. So if you go back here, everything's public here, including all the member data. We didn't make it private or protected. And the reason that we did this is that the alternative would have had to have made particle velocities a friend class of particle set, and friend classes are kind of clunky. So things are not as private as you think. Why overwork it? So finally, there's the Hockney class. This is the thing that we're providing to you. So the previous things, particle shift, particle set, particle velocities, you will write. Hockney, you'll get. So what's the Hockney interface look like? This is the only thing you'll have to know about. Hockney has a default constructor. It has a non-trivial constructor where you send in the regularized convolution kernel, the mesh spacing, and the log base 2 of the number of mesh points. And then you have an associated define function, and then finally the thing you're really going to, I mean, this is stuff I believe that we define in the driver anyway. The thing that you will use is convolve. So that's rectMD array of double applied to a right-hand side. And then there's a destructor. So you'll have to define your Hockney in the particle set constructor, because that's going to be where you'll keep track of it and hold it. A underscore kernel cur pointer and A underscore M and A underscore H are all passed through to you via the arguments. And then Hockney convolve is called in particle velocities. So this is something you will get, and all you really need to know about is that you need to be able to define it and take the arguments from the constructor and define your Hockney object. So now how do we use all of this to program ODE methods? So remember, you have RK4, which is templated on state, on right-hand side, and on increments of state. Here's what advanced looks like. And what I've done is highlighted in red the various instances of things happening to state. So for example, we initialize m delta, which is the total increment of the solution over the entire time step, and that's initialized from A state. So A state is going to know, for example, how many particles you have. So that's going to set the length of the vector in m delta. It also initializes mk, so that's an increment over a stage of Runge-Kutta, and that's going to be initialized as to what it looks like, how big is it from A state, from particle set. So these are particle shifts. These will be particle set. These functions. So this is init is part of the programming by contract that you're getting from Runge-Kutta. It's assumed that anything of type dx has an init that takes as a single argument something of type x. What about f? Well, f is something that takes as arguments something of type dx, time in dt, and something of type x, and computes a new increment. So so m underscore f is something of type capital F. And it looks like you're calling a function. Well, in fact, you are. But it's an operator data member of a class F that you're actually, it's a function member of a class F that you're actually calling. Delta, you increment So at every stage of Runge-Kutta, what you do is you accumulate the increments of the solution inside of m underscore delta. That's what you use increment for, and you multiply by a number. It's a sixth or a third, depending on what stage of Runge-Kutta you're at. And then you have, again, you are constantly evaluate right-hand side, increment, evaluate right-hand side, increment. And these are computing K2, K3, K4. And in the write-up of the homework, you will get very precise statements about what these are. These K1 through K4, and delta for that matter, are not right-hand sides. They are increments. So they have units of right-hand side times delta t. And then finally, the last statement in RK4 is to increment state by delta. So this tells you what delta is. This is where you've been accumulating 1/6 times K1 plus 1/3 times K2 plus 1/3 times K3 plus 1/6 times K4. Those have been added into delta, and then finally at the end it's time to increment x. So that's what Runge-Kutta does. One more hint as to what this is going to look like. Minus the lines, this is the sort of thing, these straight lines here. This is the sort of thing that you will see from your output. And I'll show you I'll actually demo this completely at the end of the lecture. So that's the mathematical algorithm that we have. Let's go back. Now let's talk the thing I want to spend the rest of my time on here is to talk a little bit about how I want you to organize your code, and how I want you to what the make process is going to look like. And the reason I'm going to go through this in some detail is because this is a template for what you're going to do for your projects. That here's the so I'm going to push out a directory, a homework 4 directory that will have the following things in it. It will have a source it'll have a source directory, and in fact that source directory will have 4 subdirectories: rectmd array, FFT tools, particles, and Hockney. Hockney contains all the stuff for doing your Hockney discrete convolution. RectMD array, that's the same RectMD array that you've had all along, but I'm making this self-contained. It gets pushed out. Now, FFT tools is different from the FFT tools we had before. In homework 3, you were doing things having to do with comparing performance of different kinds of 1D FFTs. And now, we're not going to do all kinds of 1D FFTs. We're just going to use FFTW. So FFT tools is going to contain FFT1D, our base class, FFT1DW, our derived class, and the multidimensional FFT, because we'll use all of them. Now, what will particles contain? Particles will contain the .h files for which you will have to input your .cpp files in that same directory. So this is where all of your code is going to get written in source/particles. Everything else is going to be provided for you. And as I said, source.hockney is going to be there. In addition to that, I also put in there a utilities directory. It contains 2 things. One, it contains the data writers for outputting what the solution looks like for this assignment, for our particle method. And in fact, we'll be putting out 2 different kinds of data. We'll put out particle data, particle locations, and we will also put out what the vorticity looks like when you deposit it on a grid at some point, at various points. So this will allow you 2 different ways of visualizing your solution. And I'll show you how both of those visualizations look at the end. The other thing I'm going to push out here in utils is timer, because that's where the timer software, ch_timer, and the other things that it needs are going to be contained. And then finally, you have exec directory, which is where main is and where you'll do all your building. So let's drill down and look at exec. Exec has 4 things in it. It has makefile, so there's only going to be one makefile here. We're not building, we have one library that's already built. We're not building libraries, so there's no dependencies like that. We have the FFTW library, but that you've already got that. So it has one makefile. It has a vortex test, which is what contains main. And now it's going to generate two directories. For this problem, it will be a directory called O2D and a directory called D2D. O2D will contain the .o files generated by the build process. D2D will contain the .d files, dependencies generated by the build process. And part of what I'm going to explain to you is what those things are and what they're doing for you. So we're going to go down. So the object files you already know, but the fact that we're putting them in one place, what's this going to do for us? Well, I'll tell you one thing it's going to do is that you no longer have to worry about well, in this case, you're only doing 2D, but if you were running 2D and 3D problems together, for the way we're going to set this up, that if this is the way it decides what this directory is it looks at the makefile definition for dim. So you can simultaneously have 2D and 3D and not worry about the object files not being remade correctly or colliding with each other, because you've stored them for permanent reference in one place. And similarly for the dependency files. So I'm going to just now walk through the makefile that you're going to be given with this. So we define home, and now I'm defining names for all the directories that I've listed here. Writers, which is where the visit writers are. RMDA, which is where the rectMD array classes are. FFT, which is where FFT tools, where the FFT classes are. Conv, which is short for convolution, which is where Hockney is. Particles is where your stuff is going to be. These are all in source or utilities, and then timer, which is where the timers are. Now I have a rather largest definition of vpath. Vpath tells gmakes where to search for file dependencies, whether it's .cpp or .h files. So we have current directory, and then the list of all these directories that we've defined here, defined names for here. Dim is equal to 2. I'm running on a Mac, so I have CXX is equal to Clang++. If you're running on a Linux system, you would replace it by G++. My code's already debugged, so I have C flags equal to -03. While you're debugging, you should probably have C flags equal to -G and -W all. That gives you all the warnings. FFTW directory, that's where you've put your FFTW software that you downloaded. Now, here's what all the flags that will be passed to the C++ compiler when you're compiling. You're using C++11, and you give it all the places where you might have include files. Now, it turns out I could have eliminated this one here, and I probably will in the file that I push out. There are no .h files in your exec directory. They are all in either the subdirectories of source or the subdirectories of util. And then all these other places are where you have places that you might need include files, including FFTW directory /include to get the ones for FFTW, FFTW3. And then I kind of ran out of space here, so I did C flags plus equals and define dim to be the value I've set it to up here. All right, let's keep moving on here. I've defined a couple of variables here. One is ODIR and the other is DDIR. This is the name for, or the string that defines the directory that I'm going to be putting the .o files and the .d files here. Notice it's O dot the value of dim and d, so that would be O dot 2D. Ultimately, I'm going to have to find some way to communicate to set a directory to be that name in my current directory, in my exec directory. Similarly for D. The only libraries I have is the FFTW library, and for FFTW3, and I have the library flag set there. Now, here's something I'm doing that's different from what you've seen before. I'm making source files as a list of all of my CPP files without any directory qualifiers. So let's unpack this definition here. So $wildcard all of these things is gather up all the files of this form, of the form these directories /star.cpp. So this is getting me all of those files. What does notdir do? Well, what notdir does is it strips off all the directory information in front of it. So now all we have is a list of .cpp files without any directory information. So let me see if I can. Yes. So I'm going to show you what that looks like. So I have a little helper in my, and I'll discuss this more later, in my makefile, in the one you will get as well, which lists which tells me, which will print out everything in source files. So I do that, and what do you see? Well, up here, you see that this is just all of my .cpp files, but without any where they're located as far as directories is concerned. Now, why can I do that? Well, the reason I can do that, and why that's going to be enough for me, is because look at how I've set vpath. What does vpath do? It tells gmake where to search for various files it's looking for, dependencies. So I've set vpath to look in all of these directories. And so as long as I tell it what the right CPP files are, it will know, look in all these directories to find those .cpp files. So that simplifies matters for other things. What about my object files? So I need a list of object files because that's what I need them to build my executable. So here's how I define them. Pattern substitution is to take the first argument, and the thing in front of that is the stem for this pattern, and then put that stem into this expression for everything in the third argument. So what this defines is all of our object files. With this definition, so this has, I'm taking foo.cpp and replacing it by, I'm taking foo.cpp and creating, instead of foo.cpp, /o.2d/foo.o. and then for all of the elements of source files. So let's go back and see, again, I go back to my little helper things. I say make, so here's the list of objects that are generated. It's list obj, not obj. Now, so you can see what it's done. It's taken every element of list source, taken the stem for this, chtimer.cpp, and made chtimer.o and prepended onto that o.2d. So this is a list of objects, and where it's going to be looking for objects is not in my exec directory, but in the subdirectory o.2d. This does a similar thing, but instead of for .o files, it does it for .d files, which are the dependency files. This defines our dependency files to be stored in the D directory. Let me defer talking about that for a little bit. What happened here? Okay. So here's the rule for making .o files. This is the next thing in the makefile. So my rule is, this is what this is what all of my .o file, what all the files that I'm making here will look like. It's the O directory slash %.o. So stem.o is given by stem.cpp. So it's this has to match to this. The stem of this has to match to this for all occurrences of things that look like something.cpp. It knows how to make. This is the rule for making the same thing with an O2D slash in front of it, prepended to that. So we have, it depends on the CPP file itself, depends on the make file, and then here are the recipes. So for a rule, you need to have dependencies and recipes. The recipe here is given below. So for each form file of the form, %.cpp, accessible to it in vpath, it knows how to make, this is the rule for making a target of the form $odir.o slash %.o. Now, I'm using CXX minus C compile over only output object file to the argument following -o. In this case, it's outputting to this thing here. That's what $ampersand is. Now, this rule also makes a file of the form $**d. $* is the stem of %.cpp, and moves it to $directory. So I'm making a .d file and moving it to the d.2d directory. So that's what making the .d file is. This is what generates it and sends it to standard out. Then I have something that looks very odd here, and then redirects that into .d and then moves it. Make directory -p is something you'll see a lot of in make files, because you want to have directories created by your make file. But if the directory is already there, make directory by itself is going to send an error. You say already have a directory by that name. -p says only make it if it isn't there already. So now, two questions you should have. First one is, what are these .d files going to be doing for us? And the second thing, what is this thing in the middle? What's that looks like? We're getting into things that are starting to look like line noise. So let me tell you first of all what the dependency files are. So farther down in the make file, there's going to be something that includes $deps. So that's the list of all things of the form d.2d / $d. In this case, that is so that's what deps is, and it's placed at the end of the make file. Each of these files, each of these things of this form, is a make file, but it only has one thing in it, which is a rule. So let's take a look at what that looks like for one of them. So this is d.2d / box.d. So here's the rule. It is o.2d / dbox.o. And what it's giving me is a set of dependencies, but no recipe. All it's saying, this is what dbox.o depends on. So what's that doing for us? It's a rule for making dbox.o, but has no recipes. The effect of including a rule like this is to add dependencies to the already existing ones, in this case for o.2d / dbox.o. So if you have, we up here already had dependencies for that. We had, it depended on dbox.cpp in the make file itself, and this adds these things as dependencies to those already existing dependencies. So again, let me go back to here, and I'll list dep, which is dependency file. Make list dep. And again, what is the dependency? The list of dependency files are d.2d, so it's looking in each of the, I've created a file for each .cpp file. I've created a .d file, which contains all the things that and I haven't created it, the C++ compiler has done this, which contains all the things, traces all the dependencies of all the headers, as well that the .cpp file depends on. So let me see if there's one other I can open up here. Let me open up. Well, what does Hockney depend on? It depends on a bunch of things here, but there are a couple of surprises that you might not have guessed. Hockney, yeah, it depends on all the things in rectMD array. I'm using rectMD array there. It depends on particles. I'm not sure why that's happening. And the thing that really mystifies, it depends on FFTs and convolution kernel. Yeah, I know why that's happening. Why does it depend on the writers? And why does it depend on particles? And the reason that happens is because this is coming in through header files I've included in Hockney and header files they include. So they may have header files included that you have forgotten about, but in fact are real dependencies there. Now it may well be that you didn't need those dependencies, but it's tracing all the dependencies of header files on header files, etc. So it's really doing a thorough job on figuring out what your dependencies are, and a job that you would not want to do by hand. So let me go back here. So now what I want to do is go back to my makefile, which is where I've been chopping this out of. And so I said there's this sed blah 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 here. What's that doing? First of all, let me go up here to Hockney. So this says o.2d/hockney.o depends on all these things here. Great. Now, why did I need this bit of Fandango here? Well, let me show you what it looks like if I take that out. So this is the command for making the .d files, where all I'm doing here is running the compiler with -mm, which makes the dependencies for me, and then redirects them to the stem.d, and then moves stem.d to ddrr. Great. So let me now try making something. Let me actually make everything. Compile. So it's going to make everything because I put the dependency of everything to be the makefile. Now, let me reopen Hockney.d. That's not what I wanted. So read it from disk, so I get the new one. So I get this without that Fandango in front. What's wrong with this? Anyone see it? If you see it, you're good, particularly in this font. I'll tell you. Instead of o.2d/hockney.o, it's just hockney.o. And the reason is, let's go back to our makefile. I'm making this inside of my exec directory. So when it's checking for dependencies, it's listing all the dependencies of a .o file that is relative to my current directory. So it's only after I've generated these dependencies that I move it to .ddir. So what this line is doing, what this thing here is doing, is editing that .d file, or the output from cxx-mm, to prepend on the first line o.2d. So let me go back to the slides and I'll walk you through that again. So here is the rule for making the .d file. Tab make directory pddir, that makes sure I have o.2d or d.2d available. Then I run cxx-mmc flags. So that's running the trace the dependencies and send it to standard out. So what does this do? This takes the output from standard out and streams it to standard in for the next program. That's the Unix pipe. What does sed do? Sed's a streaming editor for Unix systems. It uses a similar command syntax to VI, although it uses it in a way that you're streaming stuff in and you say do something. You can have one line or you can have a series of lines of commands that are really in the line editor mode for VI. So here's the sed command I've used, and this should be familiar to people who use VI. So this is the command, and you put it in quotes. It's for line 1, substitute hat, which is beginning of the line, by o.$dimd slash. / is so that it didn't get, so that the sed doesn't get confused between this as a slash ending a substitute command and wanting the real forward slash. So it takes as this thing streaming in and only takes the first line and prepends the directory I want it to be in. And then greater than takes the output from, and then it sends it to standard out. Greater than takes the output from standard out and sends it to whatever the file is on the right-hand side. Well, that's stem.d. So what I've done is I've now gotten the stem.d to have the right .o files, not the .o in exec, but a .o that's in the d.2d slash subdirectory. And then it sends it on to, it moves it to the to DDIR. So what has this done for us? Let's see. I'll show you that in a minute, but let me first finish the rule, the other important rule here. Rule for building vortex2d.exe. So vortex2d has two dependencies, or two lexical, or two strings for dependencies. One of them is GNU Makefile, so it depends on the Makefile. If I change that, I have to rebuild. And it depends on all the object files. Great. What's the recipe? It's compile, C flags, object files, libraries, and send it to vortex2d.exe. dim is equal to 2. So this depends on the Makefile and everything in the object file list. Good. The rule is to run the compiler with no .cpp files. So all it's doing is linking the object file. So main had better be in the object file, and in fact it is, because I put the directory dot in my vpath. So it compiled the .cpp file for me there as well. So I have some housekeeping utilities. Make clean, which is to remove everything, remove the executable and remove the object files and remove the dependency files. And now everything's cleaned up. Because I have my .o files and my .d files all in as subdirectories in my exec directory, this is all I have to do to clean up after myself. It's all local. List source, this is how this is a little utility that allows you to see what your make file really thinks various variables are. And it's a rule that has no dependencies, and what it does is it echoes this string. That's a Unix echo command. Echo is a Unix command. The ampersand in front of it is an instruction to make. What make will do in general is when you execute a recipe, it prints out the recipe first. Ampersand says don't do that, because all it would do is print out echo. It would print out the same thing twice, so that eliminates that. So this is how I listed my sources, listed my objects, listed my deps. I could have listed anything by putting rules like this into the Makefile. It's very handy when you're debugging Makefiles. So again, let me show you how all this hangs together. So I will start by running make clean. So here I am in my shell. No. So in my exec directory, all I have now is a make file and vortex test.cpp. Now I go down here and I run make vortex 2D. And now it's building everything from scratch because I no longer have any .o files. Everything is fine. And it built it correctly. And now, let me try building it again. Make vortex 2D. Because it has, there have been no changes to any of the dependence, the files on which vortex2d.exe depends on. All it does is it calls the link command one more time. So there's been no recompilation done here. Everything is up to date. Now let me do one more thing here. Let me make something not be up to date. So how is make doing all this? What make looks at is the timestamps of all the files involved. So the last time modified. Now you can artificially change the last time modified using the Unix command touch. So that's what I will do. I will touch /source /Hockney /Hockney.h. So that changes the timestamp on Hockney.h such that it's newer than everything else here. And let me type make again. So in this case, the make has said, oh, anything that depends on Hockney.h has to be recompiled. And it's an interesting collection. It was kind of indicated by what we saw in Hockney.d, is that write rectmd array changes has to be recompiled because of the dependence of Hockney.h on particles. The various, now it's recompiling some things, but it's not recompiling everything. We're not recompiling, for example, dbox. Dbox does not depend on Hockney.h or any of the things in Hockney.h. It just doesn't get recompiled. So this is an example of what dependencies are doing for you. They're keeping track of things that have changed. And when they change, it is very smart. It's infallibly smart, at least in the simple settings of where you're doing everything with files and not libraries. Libraries are a little harder, about figuring out what things it has to recompile and rebuild, remake. So that's why we go through all of this, and then the various pieces of indirection for putting it into O.2D and D.2D just makes things a lot cleaner, and also allows you to do things like have 2D and 3D exist simultaneously. So let's see, I still have a few minutes. So what I'm going to do now is show you what results look like. And before I do that, this is mainly going to use visit, and I just want to point out to you it's somewhere else in the lectures I had here that were distributed before class, but it's still the same information. From the directory in which you ran vortex2d.exe, you're going to generate a bunch of files, particle files and some other files, and this is how you get visit to visualize particles. You open something that'll be a part star.vtk database, and you have to reset the port because what it will do for particles, it will choose the minimum size window that spans all the particles. Well, particles are moving and the window gets bigger. So in order to kind of have a big enough window for everything at once, you set the viewport and window to 0101 and use that. And then you look at mesh, you add mesh, you draw, And then for a small number of particles, you may want to make things bigger. So let me show you how all this is going to look. So let's start by, so where am I? I have vortex2d.exe, so let me just run it. So it asks me for the log base 2 number of grid points. I'll put in 6, 64 squared. And let me do test 1. Particle refinement factor 4, it's going to ignore that. I think that's right. Let's see what happens. Let me run it a little longer. 6, 1, 4, 6. Okay, that looks like enough. All right, so now I'm going to look at what I end up with. And I have two sets of files. I have part.number.vtk, and then I have this set of files, md00 to md blah, 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 0 to md blah, 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 110. I won't look at the MD ones for this. For a single particle, it's not very interesting. But we'll look at what the particles look like. So let me do /.app. So this brings up visit. So let me open that. And it opens a family of files. It opens it as a database, knows they're all related to each other. And then I go down to mesh in add, and then in mesh, I go select mesh. So what visit is doing is it's treating a collection of particles as if it's an unstructured grid. And now I draw. Now you can't see anything. Let me go in here into mesh, change my point size to sphere, and then change my, or point type to sphere, and change my point size to 3. Is that enough? Let's see what it looks like. No, 3 is too much. 0.3. Yeah, okay, that's a very big particle. Let's go 0.1. Yeah, that's a nice size. Now, okay, so I dismiss. So I put in one particle, and now I let it move. What happens? It doesn't move at all. That's the right answer for this problem. If you have one vortex, it should not move. It doesn't exert any force on itself. And that's, for particle and cell method, there's some slightly subtle cancellations that have to happen. So this is actually a good debugging test. So let me quit out of this. And now let me do problem 2. 6, 2, 4, stopping time. We'll go again to 6. All right. Now let me go into visit again. Same routine as before. Open, add, mesh, draw, and again, I can't see much. Let me make it a sphere, and point size. Now it says point size in pixels. Let me make it 10 pixels, see what that looks like. Ah, I am seeing something here. But notice it's at the top and bottom, and I don't have enough space. So this is where I have to resize everything. Go to View, and now this goes 0, 1, 0, 1, and this one goes, 0, 1, 0, 1. Apply. Dismiss. And let's, 2 vortices, just circle around each other. That's how you know by the time you get to this point, you know you're in pretty good shape. So let me just stop here. Okay, get out of this. And now I'll show you example number 3. I've implemented all this, right? So we run 6, any other number than 2, so 3 for example. Now particle refinement factor, 4 particles in each direction per cell. Enter stopping time, 12.5. Actually runs pretty fast. Now let's see what it looks like. Open, particles, add, mesh, draw. Now again, you can see this is not great. I have to change the view. 0, 1, 0, 1, 0, 1, 0, 1. Apply. Get rid of this. Now let's watch it go round and round. So this is what happens when you have, so the vorticity in each of these blobs is 1. It's identically equal to a constant. And now they circle around each other, but they're sufficiently close to each other as they start merging. And there's lots of stuff you can read off of just looking at what's happening to the particles about kind of what the kind of kinematics of this looks like. The fact that we're getting, so for example, let me stop here. So this is at the very end. We get these very long, thin arms here. Notice that what started out to be lines that are fairly close together get stretched out a lot here and then squeezed in the other direction. It has to get squeezed in the other direction if it's stretched in one. That's incompressibility. But it's saying that it may be possible we might lose some accuracy there. And in places where we no longer have a grid, we may lose accuracy as well. So one final thing I want to show you is how let me delete this picture altogether. And I'll tell you why I had to do that in a moment. I want to look at what the vorticity field looks like itself on so I go to pseudocolor, variable 0, draw. Now, here is a problem. So the problem is that the default for outputting stuff is that the coordinates are given by the integer index of your box. So whereas the particles are all between 0 and 1, so the way the boxes are set, you can't really plot them simultaneously. I could fix it, but I probably won't in time for this assignment. But let me show you, this is what the vorticity looks like plotted on the grid. So I do the deposition, and this is just outputs what the deposition tells me what the grid thinks the vorticity is. And in fact, for this course, a grid, it does okay. The only thing to keep in mind is, up here, the vorticity was supposed to be identically equal to 1. Well, we're getting some things that are larger than 1 by a significant amount, 8%. Well, whether that's large or small depends on how it behaves with respect to mesh refinement. But again, you can pick out various qualitative things, and it's a different way of seeing both what the solution is doing, but also what the deposition operator is doing relative to how the particles are laid out. Okay, any questions on this? All right, we're at 12:30. For once, I timed the lecture well. So I'll be up in my office hours at 3 o'clock. I hope I will see some of you then.